Thank you for that introduction. So as was mentioned, I was an electrical engineer, but in my graduate studies, I've been picking up a bit more about biomechanics, as I've always been interested in this area. So I hope my talk today will not be too image processing focused, and um, I will just get into it. This is a project I've been working on as a part of my PhD thesis. Um, that started in the end of the summer, beginning of fall last year. So I will just jump straight into it. There we go. So starting off with a little bit of a background, the trapeziometacarpal, or the TMC joint, is a complex saddle-shaped joint. It's located at the base of the thumb. It's comprised of the first metacarpal bone and the trapezium. And this is a very unique joint in the sense of other joints in the hand, as it has a larger range of motion. And I've even seen a couple of articles stating that it can provide up to 40% of the hand's entire function. So when you do pinching, any sort of grasping, you are most often using this joint. And it has two main degrees of freedom, being abduction, adduction, and flexion, extension, with an axial rotation that has been found to be coupled to those two movements. And this joint has been shown to have a high prevalence of osteoarthritis. And while we know osteoarthritis is multifactorial disease, which can have effects from biochemical or biomechanical components, I'm going to be focusing more on the mechanical aspects that affect this joint. So in particular, for the TMC joint, when we talk about its mechanics, there's three main points that I want to highlight here. First being relationship between this joint and developing osteoarthritis and your occupation. So there have been various studies over the past few years that have looked at different groups and their working conditions, as well as other factors. And most have concluded that depending on the type of occupation you have throughout your life, you have a higher risk of developing osteoarthritis. And mainly they cite the reason being that you are performing repetitive movements over a long period of time throughout your life. And it has not much to do with the having high loads in your joint, in the TMC joint. And one other reason I would say this is a very interesting joint to study is that there's a lot of conflicting reports, I would say, in the literature, where some studies will claim cartilage wears in one side of the joint rather than the other, and another paper will claim the opposite based on their findings. So there's a lot of things that can be further clarified by researching this joint, and specifically looking at some of the biomechanics. Another area that is very interesting in this joint is looking at the contact forces. So while those previous studies have cited saying that the amount of load experienced by the joint doesn't necessarily cause osteoarthritis in that joint, there has been at least one that I could find interesting paper from the late 70s that claims that there can be up to 120 kilograms of applied force in the TMC joint during a forceful grasp. And finally, I just want to highlight, not just for the TMC joint, but for carpal joints in general, studying the mechanics has great implications for better understanding how implants affect the motion, looking at fractures, as well as diseases like osteoarthritis, as I mentioned. So one way that we can actually image or look at these biomechanics is using dynamic CT, which gives us three-dimensional images over time, similar to a video, like you can see two examples on the right there. And traditionally, or in the past, since its development, it's been mostly used for imaging, heart and lung, or looking at radiation therapy planning, but has been growing more in the musculoskeletal research field. So particularly when calculating joint biomechanics. And there have been various papers over the past couple of years, more and more emerging over the last, I would say, 2 or 3 years, looking at different joints and calculating various different parameters. So for example, some may be more qualitative, like the top image there from a paper in 2016, that simply calculated the change in a distance between two carpal bones during a movement. Or you could have some more papers that are a bit more quantitative, looking at joint angles, or looking at joint proximity as a surrogate for contact area and so on. So while we can image these joints using dynamic CT, you might be wondering, well, why would I, if I could just pop into your motion analysis lab, you have a much higher temporal resolution, you don't have radiation, it's much more established technique, there's much more published in this area. I think I've highlighted a couple pros and cons for each here, but I think the most important thing to note for dynamic CT, which I think gives it a little bit of an edge, is that we are able to image joints that are not normally accessible for your skin surface markers in motion analysis. So those joints such as the carpal joints or the TMC joint, as I will discuss a little bit more. So there are still a few major issues if we decide to go this route, such as the processing time. So because we're acquiring these three-dimensional images over time, the computation time can be quite high. Many papers have not provided any estimates to how much processing time they require, but one that I could find from 2018 reported 120 hours just to process a single joint for a single movement. So you can really see that if this technique is to be used in larger studies rather than experimental studies to look at a single joint or very few joints, then we need to automate these tools to process the data and make the processing time much faster. And another issue that I'd like to highlight that hasn't been really explored, at least for dynamic CT, is looking at the precision of landmarks. So if we are to calculate some joint angles, often you'll need to use some bony anatomy on your joints to develop a segment coordinate system for each segment, and then calculate your joint angles from there. And this study I've highlighted here from 1999 used, I believe it was 6 raters in a motion analysis system to see what the effects of the landmark placement, the skin surface landmark in this case, placement has on the anatomical frame orientation, as well as the resulting joint angles. And I'm highlighting this because while you see on the left figure there, you could have a orientation difference of about, say, 4 to 5 degrees, and that can result in a very large change in your joint angles. And while this paper doesn't really discuss how much they view as acceptable error or difference between your different raters, I think it's very important to understand how much difference you should be expecting before doing a larger scale study with dynamic CT. And as I mentioned, this hasn't really been examined for dynamic CT, as most studies tend to be of very small sample size and tend to just focus on quantifying normal kinematics or something like that. So those last two slides kind of lead into the objectives of this project, which were to first develop the tools needed to process these scans and aiming to develop something that is more semi-automated and is much faster than has been previously reported, as well as to examine the effects of those differing placement of landmarks has on the resulting joint angles. And a lot of this work is still underway, but I'll just cover where I'm at today. So first, to scan, we needed to scan something with the dynamic CT scanner, and we decided to go with a 10 cadaveric specimen that we obtained from the cadaver lab here at the University of Calgary. 5 were male, 5 were female, and you can see the age range there. So it was predominantly older specimen. All were right-handed. However, one had to be omitted due to severe joint degeneration that made image processing very difficult. So now that we have our samples, we had to figure out a way to actually get them to move during scanning. So we had a student come in last summer to develop a passive motion device to move thumbs of the specimen during scanning. And this was largely 3D printed and used in Arduino Uno and a servo motor to actually move the thumb. And the entire device was enclosed in a plastic bin for scanning. And the device was designed to move the hand in radial abduction-adduction movements, simply just for simplicity. So here you can see the device in motion before scanning. And the all scanning was performed at the Mojo at the University of Calgary. And you can see the scanning parameters for the dynamic CT scan here. So there are a lot of limitations, as I mentioned, for dynamic CT imaging. And you can see here the voxel size was, or the spatial resolution was quite poor, if you see the images at the bottom there. As well as the longitudinal coverage was limited to 40 millimeters. And these were just parameters that were fixed, were limited by the CT scanner itself, rather. We had plans to use a different scanner at the Foothills Medical Hospital, which would have allowed for a slice thickness of 0.625 millimeters and a coverage of 16 centimeters. But due to COVID, we weren't able to actually get access to that scanner. So we went ahead with this scanner. So as I mentioned, we had these great limitations of the resolution as well as the longitudinal coverage. And when we want to calculate, say, joint angles for the TMC joint, we actually require the full first metacarpal bone, which you can clearly see that has been cut off in the coronal image at the bottom there. So we needed a way around that, as well as this spatial resolution. You can see that in particular for older specimen, we had a narrower joint space, as well as degeneration, osteophytes, and so on, that made segmenting these images very difficult. So to get around that, we actually performed a static CT in the same scanner at a higher resolution with the full hand in the view there. And while this worked for most scans, some of our older ones also had degeneration that was enough to warrant, I think, acquiring an even higher resolution image. And you can see in this example in particular that the joint space was very narrow, that made automating any sort of image processing techniques very, very difficult. So again, since we're using cadaver specimen, and we have access to even higher resolution scanners, we opted to, in addition, get an HRP-QCT scan from the Mojo as well of the same cadaver specimen. And you can see the parameters on the left there. And what's important here is that we have a much higher resolution image that has the full first metacarpal and trapezium in the field of view. However, since we cannot fit the passive motion device, into the gantry of the Extreme CT scanner due to its size, we ended up having to process each bone separately, as we couldn't guarantee the position remained constant between the different scanners. But since we know that these bones did not change shape, we can perform registrations between each individual bone. And these high resolution images were then used for the segmentation and for the landmark selection to calculate our joint angles. And this is just an overview of the four, I guess, main steps for processing before we could actually quantify any joint kinematics. First was to perform our image segmentation, which was very difficult in our static CT due to the poor resolution and the close proximity of some osteophytes and bones. But in the HRP-QCT image was a lot easier. So we have a custom pipeline here, or script rather, that was developed in Python and using the ITK imaging library. A fixed threshold was first selected for each bone, the first metacarpal and the trapezium, and then kept constant throughout all samples. A binary Gaussian smoothing was then applied to remove some of the noise that was incorrectly classified as bone. And then there was a sequence of morphological operations that I won't go into too much detail on. And this is where the pipeline gets semi-automated rather than fully automated. Some manual corrections were needed for a few cases where the joint space was still very narrow, even in these higher resolution images. So those needed to be separated before proceeding. And then the largest component is extracted using component labeling, and some more morphological operations just tidy up the image, and we get a nice segmentation of the bone, as you can see on the right. But now, since we're in the HRP-QCT image space, we've veered so far from the dynamic CT image space that we need to find a way to get back before we can actually compute any motion from those dynamic CT videos, if you will. So the next step is to register our high resolution image to our static CT. I originally tried going directly to the dynamic CT image, but the drastic change in image quality was a little bit too much for, I guess, visually pleasing results. So by going through a more stepwise manner, as I'll show in the later slides, the results looked a lot cleaner. So we first performed a landmark initialization between the static CT and HRP-QCT, and then optimized mutual information to register the images and transformed our image mask. So you can see the results here were quite nice, and while I don't have an image of what the segmentation in the static CT looked like, I can just say that it did look a lot nicer using this longer approach. And then finally, we needed to move this into our dynamic CT images, which again was done performing a image registration. However, this time optimizing the correlation between the static CT and dynamic CT. And you can see the result here. So the reason why these masks needed to be translated all the way into the dynamic CT image space will become apparent in the next few slides. So just bear with me. And finally, the dynamic CT images needed to be registered between the frames so that we could actually calculate the motion, the change in orientation of the bones throughout the entire motion that we scanned. So to do this, we use those previous masks that are now in the dynamic CT image space to crop out the bones that we are processing individually. Because we had so many image frames, I believe there's about 60 per dynamic CT image or video. Individually cropping those would be very tedious and take a very long time. So using that transformed mask, we're able to dilate it and mask out the bones of interest, and then finish our registration between each dynamic CT frame. And now that we have that entire processing pipeline completed, we need to actually calculate the joint motion. So there's many different ways that you can calculate joint angles, helical axis representations, fixed axis sequences, and so on. For the TMC joint, I decided to stick with a joint coordinate system representation, as the fixed axis sequence that was described in the 1980s had a few issues with it that were outlined in some of the other papers I've cited here. And the joint coordinate system also has various benefits, such as the sequence dependence of the individual angles. However, there is an ISB standardization that was proposed by Wu et al. In 2005, and they attempted to propose a joint coordinate system standardization for every joint in the body. But it was further expanded on in 2009 in this paper here that proposed a slight modification to their mobile axis sequence, that reduced the kinematic crosstalk specifically for the TMC joint. So as you can see in the figures I've highlighted at the bottom here, the new axis sequence that was proposed in this paper is shown in the dark solid black line. And you can see that for the motion they performed of a flexion movement, you can see that they had a slightly higher amplitude for the flexion angle, as well as a reduction in the internal-external rotation, which they cited as being mostly due to joint laxity. So this is where I ended up landing on for which way to represent the joint motion for these joints. And that was mainly due to this reduction in kinematic crosstalk. So now to actually calculate this or set up this joint coordinate system and calculate the joint angles, there's even more steps that we need to go through. First being to select the landmarks on the bony anatomy, and then to transform those points to our CT image space, set up the segment coordinate systems and the joint coordinate system, and finally calculate these angles. So to select these bony landmarks, this was done on the higher resolution images, as it was easier to identify which landmarks needed to be selected. Some of them were not able to be as clear in the lower resolution images. And this was all performed in a GUI or a viewer that I developed using Python and VTK to visualize these dynamic CT images as well as other CT images and select these landmarks. So here you can just see a description of some of those landmarks that were originally defined in the ISB standardization. So there's 3 for the first metacarpal and 4 for the trapezium, but I won't go into too much detail on those. And then next is using those transformations that we obtained from that lengthy post-processing pipeline I described earlier, we are able to move those points into the CT image space. And then finally, we need to set up the segment coordinate system before we can even calculate these joint angles. So the segment coordinate system, as I mentioned, was defined using that slightly modified mobile axis sequence from 2009 and has each of the coordinate systems centered at the center of the first metacarpal and trapezium joint surfaces. And then for our joint coordinate system, you can see that the axes that were chosen as follows. For our first fixed axis, we went with the trapezium z-axis, as that is the flexion extension axis. For our second fixed body axis, denoted as E3, that was the x-axis of the first metacarpal, as that represented abduction adduction. And then the cross product of those two was our floating axis that had axial rotation about it. And the neutral position was defined as the alignment of the first metacarpal and trapezium segment coordinate systems such that the angle between them was 0. So for calculating the joint angles, this is also where the joint masks came into play. Now that we had the masks available in each dynamic CT image frame, we were able to calculate the inertial frame, or inertial axis, sorry, for each segment using those masks, and then calculate the transform to change the orientation of the inertial frame into the segment coordinate system frame of the first frame of the dynamic CT image. And since we know these bones shouldn't be changing in shape, we know that this should be a fixed transformation, meaning that for each frame, the transformation that changes the orientation of the inertial frame to the segment coordinate system frame should be the same. So using that information, we are then able to calculate the motion of the first metacarpal relative to the trapezium in each frame, and it's relatively fast compared to previous studies that I've seen. And then now we can move into the reproducibility analysis, so that now that we have a method to take these scans and quantify the joint motion, we have 3 raters that selected landmarks on the HRPQCT images using the previously described viewer. And a manual was provided to each of the raters with a description of which landmarks they should be looking for. And the scans were randomized between each rater such that the same order of scans was not used when selecting points. And here, what I like to compare is the positioning of the landmark between each of the raters, the orientation of the segment coordinate system for each segment as a result of the differing landmark positions, and finally, how those affect the resulting joint angles. So yeah, here you can just see an example of the segment coordinate system orientation differences between 2 raters. And while a lot of this calculations are still underway, I can present some of the more preliminary results here. For the segment coordinate system orientation between raters, for the first and the second rater, you can see here that we had a slightly higher difference in orientation angle in the trapezium compared to the first metacarpal. And it doesn't seem too high, but when we look at the difference between rater 3 and the other 2 raters, we can see that this difference is a lot larger. So while we have somewhere from 1 to 3 degrees in the first metacarpal, depending on which axis we're looking at, you can see a much higher difference, even reaching close to 9 degrees in the case of the Y segment coordinate system for the trapezium. So while I don't have the results to show how this affects the joint angles as of yet, I think it's so important to understand why we might be seeing such a big difference in these two segments of the TMC joint. So I think this is mainly due to just the way the trapezium was in these scans. Because we had a higher age of our specimen, these tended to be of poorer quality. And by poorer quality, I mean they had more degeneration, more osteophyte formation, which led to more variability in the shape, which might have made it more difficult to identify the same location if the shape changes drastically between specimen. Also, the difference in landmark position was also a lot greater for the trapezium compared to the first metacarpal, and more particularly in the tubercle of the distal radial tubercle of the trapezium, which you can see highlighted on the right there. So if we look at it from a radial perspective, as is on the bottom, it might be difficult to decide on the very rightmost edge there if you should be placing it on the inflection point of the tubercle or on the top of the surface. So I think that's where a lot of variability came into play as well. As I said, the joint angle results are still being processed, as there's a lot of data to go through. In addition to the dynamic CT scans for each of the 9 cadaveric specimen, we also perform scan-rescans to test the scan-rescan reliability of the passive motion device. So I think in total there's close to 2,000 images to go through, so quite a bit. And another thing that I'd like to look at once the joint angle computations are complete is trying to look at if the intra-rater comparison of the landmark positioning is going to be improved, and I would guess that it will be a lot better. And as I mentioned in some of the earlier slides, there's a lot of issues with artifacts from both motion analysis, and there's different errors that we can experience in dynamic CT. And in this case, we can expect lots of errors from the image registration. As we're doing lots of registration and transformations, we can expect that that should have some effect as well. So I didn't have an image in this presentation, but in the platform of that passive motion device, there is 3 holes that are drilled of a fixed size at the bottom that we can use as fixed landmarks to look at the registration error between dynamic CT frames as well as CT to dynamic CT registration. And finally, another thing that I would like to look at with this data set is that whether the static CT images can still be used for the landmark selection, and if the difference in landmark positioning between raters is going to be greater than the HRPQCT or high resolution images, and what effect that's going to have on the joint angles. But with that, I'd just like to acknowledge my supervisor, Dr. Sarah Mansky, Kendra Wang, who designed the passive motion device, and Dr. Justin Say, who is a postdoc in our lab, who helped out a lot with the scanning, and my supervisory committee, staff at the cadaver lab at the University of Calgary, and the Mojo imaging staff. And with that, I am happy to take any of your questions. Yeah, thank you.
Thank you, Michael. And actually, my apologies about the noise from my microphone.
Oh, that's okay.
So how does it sound now? Is it better than before?
Sounds good to me.
Okay. If you start hearing again, just shoot me a message and then I'll just switch my microphone. So before we get to the discussion started, I would like to gently encourage you to turn on your camera during the discussion period if you are comfortable with it. And I think it'll give us a more active discussion period. Thank you very much. If you have any questions to our speaker, please click the icon raise hand buttons. Since it seems that Zoom has been updated, and to me, it seems like a few things changed. So let me quickly explain where the button is. So if your Zoom is the latest version, then please go click reaction icon at the bottom of your Zoom screen. Then you will see a raise hand button in addition to multiple icons there. But if you've been using any previous version of Zoom, then please go click participants and And then at the bottom of your screen, then you will see the blue icon labeled as raise hand at the bottom on the right-hand side. Also, if you cannot find any of it, then please feel free to quickly send me a message. Then I'll call on you when it's your turn. Now I'll open the seminar to the questions. Yes, Brent, please go ahead.
Thanks, Mike. And thanks, Sungwon. I was freaking out. I couldn't find that hand, so I found it. Okay, very important question first, right off the bat. Is anybody in that lab photo of yours photoshopped in?
No.
So that's a legit background?
That's a legit photo, yeah.
Okay. It looked a little bit photoshopped to me, so it's just actually a perfect photo. Okay, so now a different question. I want to know about the optimization approach.
Yeah.
So what is it doing? You know, you've got this STL file, you've got the, and maybe if you could just focus on one frame, because I know it's probably a static type of optimization. You do an optimization for one frame and then you move to the next frame, I'm assuming. So what is it trying to do with the STL file and the X-ray?
Right, so you're referring, just to clarify, to the registration between, say, some of the CT images. Okay, so in the case of the HRPQ-CT, or the higher resolution CT image, to the static CT image, in this case, we are looking at mutual information. So we are trying to not optimize anything with the STL or mask file. We're actually doing an optimization of the grayscale images themselves. So with the mutual information, we are looking at maximizing, in this case, areas of the image that have the same information. So while they may not have the same intensities, they have similar information in respect to their own images. So this is a technique that's most often used between multimodal images like MRI to CT. But I found it worked really well for high resolution to lower resolution CT image, as opposed to something you'd more traditionally expect, like mean square error or a correlation coefficient or something like that.
Okay, so it's actually taking the whole grayscale image from the static scan, no segmentation required, but it's taking the whole grayscale image from the static scan, and then it's doing some kind of cross correlation with the dynamic scan, and then it's like settling on the maximal correlation or something
exactly
like that.
Yeah, so in the case of the dynamic CT images, that's exactly what it's doing. It's just matching the images based on where the correlation is minimized in this case, or I think they use like a negative in their optimization, something funny in ITK. But yeah, you're essentially right. And then the transformation that goes from those CT images is then used to transform the masks.
Right.
Yeah.
But you only make one mask, right? You make the mask from the high res.
One. Exactly.
I see. Okay, yeah, all right, that makes sense to me. So then the error that you present, where the intra rater error, that has nothing to do with the optimization itself, right? There's this is the optimization is one thing, and then this is just how the raters identify those landmarks.
Exactly. Yeah, that optimization is a little bit separate. That's something in like the next little while that I'll be working on, as I haven't gotten to that point yet. The processing time took me a lot longer than I expected. But yeah, the differences here are just in the segment coordinate system, the difference in angles between the segment coordinate system axes due to the different landmark positions selected by the raters, if that makes sense.
Yeah, it makes sense. But or not, but where how it says delta X, delta Y, delta Z here, are you reporting changes in angle from frame to frame, or is that really you're just saying it's the difference?
This was just purely the difference of the segment coordinate system in the first frame.
Okay, so
this wasn't a joint angle between frames yet.
Okay, so do you think that if you looked at the change in angles, so not necessarily the difference in the absolute angle between raters, but the change in angle, and so the velocity, the angular velocity and the angular acceleration later on, which might be important, do you think that the changes in the angles would be actually have better reliability than the absolute angles? Or do you expect similar type of errors with the changes in angles.
And by change, you mean between the dynamic CT frames, right?
Yeah.
I'm not too sure what to expect from that aspect yet. I think that the results I'm just showing here is just more like preliminary. How do the different landmarks change the segment coordinate system, which should be the same in each scan, independent of the rater. So if we're looking at, I think we'd have more issues when we're talking about between frames, as we have an additional step where we're doing another transformation. So originally my plan for transforming between the frames was actually to use the registration or the transformation that resulted from the registration of between frames. But I opted to go with the method I described here, knowing that the change in the orientation of the inertial axis to the segment coordinate system should be fixed between each frame. But I'm not entirely sure how much error to expect as of yet. I'm hoping I'll figure that out in the coming days and weeks.
And then when you say inertial axes, just so I have this right, do you mean like the moment of inertia?
Yeah.
So like the principal axes of inertia of the bone?
Exactly.
Itself?
Exactly.
Okay, thanks.
Thanks.
Okay, if there be any questions for our speakers? Actually, I have a couple questions for you, Michael.
Sure.
So sorry, I might have missed in the very much beginning, but could you explain once more that why you choose the thumb joint rather than other joints for the study?
Yes. So this is more of like I guess like a smaller subset of a larger study that I'm doing, looking at osteoarthritis in this joint. So we know it affects the TMC joint quite often. You can argue, some papers have said it's the second most common or third most common joint that experiences osteoarthritis. And the reason why I think it is also very interesting is that it's not really easy to image using motion analysis systems, because you can't put surface markers on the trapezium as it's in your wrist. So that's where I think dynamic CT really excels, is it gives us an opportunity to image joints that we can't normally look at. But the reason why I chose TMC is mainly because that's part of my overall thesis. A lot of other studies have done carpal joints as well to look at like non-unions and other pre and post surgery assessments and so on. So it's another area in the hand that you can look at using dynamic CT. But yeah, this is just for my project.
So do you have like a future plans to look at other joints using your methodology that you are developing?
So for my thesis, the plan is more to stick with the TMC joint, but the goal of the processing steps that that I developed is that they can be applied to other joints as well. So in terms of what you would actually need to change if you switched from, say, the thumb to the knee or something like that, you would need to change maybe the number of landmarks that you're using and exactly how the segment coordinate system is defined. So for now, I just take in the raw points, and then knowing which points to connect and which cross products to take, I can develop the segment coordinate system for each hand. So that would just probably have to change. But the rest, the goal is to have it to work for other joints as well.
Thank you.
Thanks.
I still have a few more minutes for questions. Yes, Alia, please go ahead.
Hi, Michael. I was wondering, for the cadavers, did you purposefully choose the age range, or were those the age ranges that you were able to get access to?
So it was the latter in that case. That was what I had access to. The first one was actually the one that we had to remove from the study due to the degeneration, and it was from it was a 104-year-old specimen, or from a 104-year-old donor. So there's just not too much availability, and due to COVID and everything, it was a little bit difficult to wait around for more and not be able to potentially scan. So yeah.
Thank you.
Thanks.
Brent, please go ahead.
I'm just gonna keep asking questions if nobody has any.
That's fine.
I wasn't super impressed with the captured volume that we're able to do at Mojo. nor am I super impressed with the resolution
Yes.
that we're able to do a Mojo. I can't imagine being able to use this for the ankle or the knee or
Exactly.
so. Is there anything that can be done with this scanner to make it better?
So no, not really. This is basically the best that scanner can do. There is another scanner, as I mentioned, in Foothills Medical Center that can give
Yeah.
you 16 centimeters and a much better resolution. And I believe Murray from Dr. Prism Schneider's group actually used that scanner for his ankle study looking at the ankle joint. So that was the plan, but due to COVID, we got stuck with this. But at the very least, I think that if we have the general motion of the joint from this lower resolution, smaller coverage scan, then we can just get the masks from a higher resolution and just use the orientation information from this scan. At least that's kind of the plan for now.
Yeah, the challenging thing with this kind of resolution is sort of believing the accuracy of the image registration
Yes.
approach. And depending on the research question that you have, I wonder if, it makes just as much sense to take two static images, where they have their hand in one position and then you put it in another position, and you could use the robot to passively move it. But so even if you slow down the frame rate, you couldn't get a better resolution or a different or a larger capture volume.
It wasn't much better in terms of resolution, and the coverage was the highest it could go. So that was really limited, and you could try taking several static images, but the arguments I've seen against that and for dynamic CTs, when we're particularly looking for quantifying some kind of kinematics in a joint that has some sort of disease or has a fracture and things like that, where you might be missing some sort of minor like movement or something like that, if I'm being clear enough. So previous studies have, a lot of studies that I've based the decisions for joint coordinate systems and so on have been, as you said, static images acquired in sequence. But I still think that you might be missing something in the actual joint when we're talking about something like, say, a joint with osteoarthritis or so on.
Yeah, okay. And then maybe just the last question on this topic, that image that I'm looking at right now, the coronal view.
Yes.
Is that an arthritic joint or is that a normal joint and it's the resolution?
This was a very old joint, so the joint space was very narrow. I had a few others that you could actually tell the difference between the trapezium and the first metacarpal. A real big limitation for this is that the cadaveric specimens were mostly older. There was a few that were a little bit younger, and I could argue that maybe if you put in the time and effort to segment the dynamic CT images, you'd probably be fine doing that. But for the most part, we had older specimen.
Okay.
Yeah.
Thanks.
Michael, I also actually have a couple more questions.
Yes.
So you used cadaveric specimen for your testing.
Yes.
So since I'm not really familiar with this field yet, so would you expect to see some difference between this cadaveric data and compared to if you are actually doing on human in vivo testing?
Yes, definitely. So there's a lot of differences that I think we can expect. First being that this tissue was frozen and then thawed. So that's going to have some effect on the tissue itself. And another big factor is that we're using this passive motion device. So you can argue that while you can perform the same movement in vivo, you're kind of restricting the motion with this device. So there's quite a few differences, I would say, between in vivo and with this what I've outlined here with the cadaveric specimen, but I think the important point is that we weren't trying to compare in vivo or healthy movement to what we saw here. This was more to set up the protocols for imaging, to set up the processing pipelines, and then to look at the reproducibility of some of the tools as well.
Also, another question that I had is that, so I'm a more like a knee person. So
Yes.
whenever I open the knee joint of rabbits, I always see, I've been observed a lot of variance among the individual rabbits. So is that be like a similar case that you have? Like whenever you do the testing on different specimens, have you observed a lot of variance between each specimen?
What do you mean for
Like different
variation?
Structures? Like,
different structures?
Yes.
Okay. Well, I mean, in terms of the bones themselves, there was a lot of variation. As I mentioned, some had clearly had, say, rheumatoid arthritis or osteoarthritis. There was formation of osteophytes presence rather. Some bone erosions, joint space narrowing. So especially when we're comparing some of the older specimen to some of the younger ones, it was pretty clear there's a big difference in the bone morphology itself even. So. Yeah.
Thank you. Yes, Art, please go ahead.
Yeah, my question is about the humans that you used for, inter-rater reliability and stuff like that.
Yes.
And the basic question is, how good are humans at doing this?
So that's kind of what I was trying to answer. So I've seen previous studies that used either static or dynamic CT, and instead they used helical axes, but they had a similar process for developing these segment coordinate systems. And one group actually proposed an automated way to set up your segment coordinate system in this joint, citing that humans can't be reliable. But I kind of wanted to answer the question of, well, how reliable are we? So that's kind of the main purpose of the reproducibility study here. And unfortunately, I don't have the effects of the joint angle results from that. Hopefully I will soon, but even just looking at how the segment coordinate system changes in static frames, we can still see that in some cases when we have more changes in the shape of the trapezium, we can actually have very large differences in our segment coordinate system. So I think I don't have an answer as to how good or bad we are, but I think I would say that we are not that great.
Well,
and if we can't automate it, I think we should.
Yeah, it seems like you have more than that, because for your automated method, you have this mutual information measure. So then have you tested not just the reliability of the coordinate systems
Yes.
that people come up with, but you could just rate people on, do they optimize the mutual information better or not as well as the automated algorithm?
Well, that registration was all automated, so there was no user interaction. So that should have been the same for all. Yeah.
Well, then is there some other measure that you could do? So reliability is a matter of, did people choose the right, similar answers, but that's
Yes.
not the same thing as people choose the right answer. So then
Yes.
is there a measure that can be formed of how, you're trying to optimize something, even if you're a human who knows what they're doing, but they're trying to make something match. So then is there a measure for that?
Yes. So I don't have anything set up with the current scans that I have to test something like that. But what we could do is, if we acquired like another cadaver and we actually like dissected it and put in some markers on the exact points, whether that is just based on what we think is right, or what if we actually can get, say, like a hand surgeon or something like that to determine the exact location of where it should be. Then if we can do a similar scanning technique like we did here, then we can actually test, what the degree to which how close people are to the actual, I guess, right answer for the landmarks.
Great, thanks.
Brent, please go ahead.
I just wanted to say, and I apologize if I've talked to you about this before, but I feel like this is screaming for a statistical shape modeling approach. And
Yes.
you take the person completely out of the scenario and identifying these landmarks. It wouldn't take long to have a template thumb bone where you have identified what you are saying these landmarks are, and to just morph all of the new bones into that, system, and automatically you have, what you're going to call these anatomical landmarks. So if you're not planning to do that for your PhD, I'd sort of push back and say you should.
Well, I absolutely agree with what you're saying. If I have time, I would absolutely love to do that because I think that is the right way to go. With the dynamic CT images we have here, we wouldn't be able to do it, but I think from the static CT images, we would,
Yeah.
and then transform those over. I absolutely agree that that is the way to go in the future. I just hope I'll have time to get to that.
Olivia has workflows now for the tibia and the fibula.
Awesome.
So maybe she would be willing to chat with you about that.
Definitely, we should set up a meeting.